At that point, we'll be sure and put this out on the YouTube training channel. This recorded session, we'll put it out on the YouTube training channel, and we'll be calling it session number 2, and then today's date. So you can identify that out there on the YouTube channel. It'll be today's date along with session 2. So anyway, so we are recording at this point. Let me go ahead and I'm going to go ahead and shut my camera off temporarily. That gives us a little better streaming. And then we'll go ahead and share my screen, and we'll get everybody squared away here. Okay. And let's see here, we'll get our PowerPoint pulled up. Okay, everyone should be able to see the PowerPoint okay. And again, if you do have some good questions, go ahead and unmute your mic and ask that question. And then we'll go ahead and answer questions as we go along. But anyway, good morning, everyone. Again, my name's Joel Lunsford, and we're really glad to be training with you this morning. Today, we're going to be doing session number 2, furnace overview, specifically around the TMY furnace control board. Now, it could be a TM9Y, which would be the high efficiency furnace, or it could be a TM8Y, which is the 80% furnace. But either way, the control board is going to be the same, and all the stuff that we talk about will apply to both boards, both furnaces, both model of furnaces. And so today we're going to be reviewing the gas furnace control board again, and some of the things we're going to be talking about specifically will be the control board layout. Now, team, we're going to actually go over every input and output on that board. We're going to talk about field selection of heating off delay timings, as well as low voltage terminal wiring. And so literally every thermostat wire and where it lands on that board we're going to be discussing this morning. We're going to talk about airflow adjustments, and then finally, towards the end of the session, we're going to have testing flame current. Now, I've decided to add the testing flame current to each one of our furnace modules that we're doing. I know the last time we did our training session, we talked about testing flame current, but it's kind of one of those things that if you missed the session before, or if there's someone new to the session today, we'll go ahead and continue to talk about testing flame current on all of our modules, just in case someone missed it the time before or it's new to you. So as you take a look at your 2-stage control board, now this is a 2-stage heat, 2-stage cool, and again, this board will be found on the TM8 and 9Y products. Now, it does use a high efficiency blower motor, but the neat thing about this board, it's got some really cool functions that I think you're going to enjoy when we start getting into especially some staging functions, because this board, even though it's a 2-stage heat, 2-stage cool board, it has the unique capability of allowing single-stage thermostat operation, which is really kind of neat. And that's really some of the things I like about our Johnson Controls Champion furnace products in general, is the fact even if you're stuck with a single-stage thermostat, we can still give you some staging function. And so unlike our competitors, where if you just jumper, W1 and W2, you have a 10-minute time delay between first and second stage, and that's all you get. Well, on our Champion products, if you have a 2-stage heating product or 2-stage furnace product on our Champion furnaces, we give you some staging capability by moving some dip switches. And so we always encourage you to use a 2-stage thermostat on a 2-stage product for the ultimate comfort and the ultimate control on the product. But we also know the reality in the field is the fact that sometimes you're just stuck with a single-stage thermostat, or maybe you don't have enough wires behind the wall, or whatever the case may be. So with our Champion product here, we can give you some staging capability, and so we'll talk about that here shortly. But let's talk about our low-voltage thermostat wiring first. If you'll take a look at the photo on the PowerPoint, you're going to notice on the left-hand side, you're going to have your terminal strip for your thermostat. So let's go over that one by one, just to make sure everybody's squared away. So starting at the top of the terminal strip, we see Y1. That'll be our first stage cooling call if we have a 2-stage piece of equipment outside. And by the way, let me take just a second or two as well on this. This is one of the most versatile furnaces we have in our inventory. It's a great furnace, and it has a high efficiency blower motor on it. and it's literally compatible with anything in our inventory except our Momentum 20 and 21 SEER product. Let me say that again. This thing will match up with anything in our inventory with the exception of the Momentum 20 and 21 SEER product. So if you have a 19 SEER 2-stage or a 17 SEER 2-stage or a TH16 5-stage heat pump, it'll match up with it. And so it's a very, very versatile product. It's a good furnace. As a matter of fact, if I had natural gas on my property, this is probably the furnace I would put in. I really, really like the features of this furnace. So Y1 is our first stage cooling call. Y2 will be our second stage cooling call if we have a 2-stage product outside. W1 is our first stage heating call. Now remember, team, this is a 2-stage heat, 2-stage cool board. So if you're stuck with a single stage thermostat, you always want to land that W call from the thermostat on this W/W1 terminal. And the reason that is we can give you some staging a little bit on later on with some dip switches. So if you do have a single stage thermostat, just land your W wire on this W/W1 terminal. If you have a 2-stage thermostat, W2 will be our second stage heating call from the thermostat. Ours 24 volt hot. That's very, very common in the industry. Ours 24 volt hot. Is our fan call from the thermostat. So if we want to have fan operation, we can energize the fan call on the thermostat sub-base assembly. So G is our fan call. And then finally, C is 24 volt common. Any questions or comments on the basic low voltage wiring so far? Everybody good? Okay, as we move around the top of the board, we see that we have a last error button. This last error button allows you to retrieve flash codes and to relate and to bring up flash codes and last errors. Now remember, team, this board will remember the last 5 errors on the board, the last 5, and then you can cycle through that last error button by depressing the button and cycling through your last 5 errors. Now, if you want to reset the memory, you just hold that last error button down about 5 to 10 seconds, and it'll clear the memory out of, that service memory of those last errors. Right next to the last error button, we have a status LED. Now, it should be noted this LED will flash error codes if you have error codes, but it will also show you normal operation. And if you take a look at the service information that comes with the equipment, in the install information that comes with the equipment, you'll be able to read about all those flash codes as far as the different flash codes and what they mean. Now, it should be noted that LED will flash either green, yellow, actually, I believe the service manual calls it amber, but it looks yellow to me. So green, yellow, or red. So that tricolor LED is designed to flash 3 colors. And so we just have that single LED right there on the board. So it's very, very handy. The technician can look at that. He can not only see existing flash codes, he can also find out the last 5 errors if he depresses that last error button right next to it. Any questions or comments on that? Okay.
When you say the last 5 errors, when you press the last error button, does it immediately show you the most recent error, or does it show you all 5 of the last errors in a row?
That's an excellent question. What it will do is it'll show you the most recent one, and then if you depress it again, it'll show you the next one, and so on. So, but the most recent will always be at the very top of the stack, so to speak. That's a good question. And then you can continue going through those error codes by depressing that button. And then if you hold the button down for 5 to 10 seconds, it'll clear that memory. Good question. Any other good questions or comments? Okay, good. Excellent. Okay, as we move around the board, we see we have what we call continuous speed. And what that is, that's a continuous fan on speed selection. So what this does, this allows you to select a particular motor speed for continuous fan operation team. So basically, here's what happens if the homeowner or the customer goes over to the thermostat sub-base assembly and they switch the fan from auto to on. How fast does the fan run? That's what those selections are. And you can select low heating speed, high heating speed, low cooling speed, or high cooling speed as your continuous fan operation. Now remember, if you have a call for cooling or a call for heating, what will happen is the board will override that. So this is strictly a continuous fan speed if there's no call on the board at all, except when the homeowner goes to the fan on position from auto to on the sub-base assembly. So this is continuous fan speed operation that gives you some options other than just on or off. And so unlike our competitors, to where if you have a G call on most of our competitors, if you have a G call only for fan operation, the fan will either run at 100% cooling or it'll run at 50% cooling based on the manufacturer. So we give you some nice little options there to actually select what fan speed you want it to run on with a continuous fan speed. And remember, team, where this becomes really, really neat is because if a homeowner has some IAQ products, maybe some electronic air cleaners or some media type air cleaners or some UV lights or what have you, this allows them to run the fan continuously at a nice low speed if they want to keep that air moving and filtering in the home. And especially now, with all the concerns we have with indoor air quality, more and more homeowners are looking at indoor air quality products. And so to have a furnace to where you can actually customize that continuous fan speed is a pretty nice feature. Right next to that is our heating blower off delay selection. Now, normally, team, what we do is we ship these at about 120 seconds. But what this is the amount of time the indoor blower runs after the call for heat goes away. So as you well know, that once the call for heat goes away, the indoor fan continues to run a little while to distribute the heat off the heat exchanger into the conditioned space, because there's no reason to waste that heat, but also it cools the heat exchanger down. So this is field selectable on how long that fan runs after the call for heat goes away. Now, typically from the factory, we set them up at 120 seconds. But as you can see from the dip switch selection, you can go down to 60 seconds, which is still perfectly safe for the furnace as far as cooling the heat exchanger down. Or you can go up to 180 seconds to get all the heat off that heat exchanger. It makes it a little bit more efficient. So really, this is kind of a comfort setting. If you have a homeowner that's real sensitive to temperature, and they're real sensitive to like that cool air coming out of the registers and stuff like that, set it down to 60. If you have someone that's, let's say you have a doctor that works in a cold emergency room all the time and he could care less, then the ultimate efficiency and cool down would be at 180 seconds. When in doubt, just leave it alone. If there's no complaints, I normally just leave it at the factory setting, but you do have the option of having that blower off delay adjustment field selectable from 60 to 180 seconds. Any questions or comments on those two banks of dip switches so far? Everybody good? Okay, well, right next to it, this is one set of adjustments that I really, really like about this board. What this is our heating staging if a single stage thermostat is used. So let me say this one more time. Let's say you're stuck with a single stage thermostat. I mean, you don't have enough wires behind the wall. Maybe the homeowner just loves that old Honeywell round Mercury thermostat. And yes, it would work fine with an old Mercury thermostat, single stage thermostat. So what I'm saying, if you're stuck with a single stage thermostat for whatever reason, what we can do is we can give you some staging by manipulating these dip switches. Now, it should be noted, if both dip switches are in the off position, if they're in the off position, you get no staging beyond first stage. So this is important. If you're stuck with a single stage thermostat and those dip switches are in the off position, you'll never get out of first stage. However, you have a 10 option, that's a 10-minute option. You can notice if you have one dip switch up and one down, that gives you the one on the left is up and the one on the right is down. That gives you 10 minutes between first and second stage. So if you're stuck with a single stage thermostat and I get a W call on W/W1, that our heating terminal, 10 minutes later, if it's in the 10 position, 10 minutes later, it'll bring second stage on to satisfy the heating call. If it's in the 20 position, it's 20 minutes. Now watch this. There's an auto position as well. If the left dip switch is down and the right dip switch is up, as you take a look at the little screen print there on the board, if it's in the auto position, and we have a single stage thermostat input on W/W1, if it's in the auto position, what's going to happen is the board will start looking at thermostat activity. In other words, how long it takes to satisfy from the last couple or three calls. It'll look at how long it takes to satisfy the thermostat as far as time is concerned. And it will then start making intelligent decisions. The board has got some algorithms in there. It'll start making intelligent decisions on when to stage second stage. So isn't that cool? So the board actually becomes a smart staging control if it's in the auto position. And so it's really, really important, you know, that if you have a single stage thermostat, I recommend put it in the auto position and let the board make some intelligent decisions. However, if you want to have just a 10-minute delay between first and second stage, you can manipulate your dip switches. Or if you want 20 minutes between them, that's fine too. But please remember, please make a note of this. If you have a single stage thermostat, do not put those switches in the off position, because if you do, you'll never get past first stage. And so anyway, that's our staging capability on these boards. A really, really nice feature, other than just you know, jumping W1 and W2 and hoping for the best. But any questions or comments on those staging dip switches and how they work? Okay, well, let's go ahead and work around the board then. As we come over to the right-hand side of the board, we have some blower speed tap selections. And this is where you're actually going to select your speed taps for low heat and high heat, low cool and high cool if you have a two-stage piece of equipment outside. And so this is a pretty straightforward. Now, it should be noted, team, remember, on all of our high efficiency blower motors, whether it's a furnace or an air handler, that high efficiency blower motor has power to it all the time, has line voltage to it all the time. And then we're going to command that motor what to do by providing a low voltage input to it. So even though those speed taps are, you know, high heat, low heat, high cool, low cool, and so on, those speed taps are actually 24-volt outputs from the board to tell that high efficiency motor what to do. So low heat and high heat and low cool and high cool will be 24-volt outputs from the board down to that high efficiency ECM type motor. Now, when we talk about ECM motor, we're talking about an electronically commutated motor, which is just a fancy name for a high efficiency motor. But they differ from a capacitor style motor in the fact that they have power to them all the time, and then we provide a 24-volt input to that motor to tell it what to do. So as we come down on the right-hand side of the board, we see we have 120-volt output for an EAC. That's for an electronic air cleaner. And so anytime the fan is running, that terminal will be energized with 120-volt for an electronic air cleaner if so desired. You'll notice we put a little red rubber ball, so to speak, on there just to remind you that it is high voltage, and it does not come from the factory with anything hooked up to that. That's why we put that little insulator ball on there for safety. But if you remove that, you'll find a terminal underneath that you can hook up for an electronic air cleaner anytime the fan is running, if so desired. Right below that, we have a 120-volt, what we call CIRC terminal. That's that 120-volt output to the motor all the time. Remember, a high-efficiency motor, an ECM type of motor, is going to have power to it all the time, and that's where we do it with that 120-volt CIRC terminal. Right below that, we have a 120-volt input to the board for all of our high-voltage components. And so the power coming from the power source, this power in the furnace up, will hook up to L1 on the board right there. Right below him, we have a 120 volt input. It's called XFMR. That's for the primary side of the transformer. And so that 120 volts will be fed to the transformer primary on that terminal. And then finally, we have a 120 volt humidifier terminal down below. And so if you want to run a humidifier, you'll have an isolated relay output off the board to give you 120 volt output anytime we have a heating call. So anytime there's a heating call on the board or a W call on the board, we will output 120 volt on that Hume terminal to operate a humidifier if so desired. Any questions or comments on the motor speed taps and our line voltage components so far? Everybody good? Okay. As we move down the board, we see that we've got some neutral terminals, and those neutral terminals are kind of color-coded white, just to kind of remind the technician that all of those neutrals, that would be where your white wires are going to come in. So the other side of your transformer, that white wire on the primary side of your transformer, it'll hook in there. You know, the neutral terminal for the motor will hook in there, and so on. You get the idea. So that neutral bus, they're all tied together electrically, and so it doesn't matter which terminal you use because they're all just tied together. If you look at the back of the board, there's just a solid piece of metal back there for those neutral terminal bus. As we come along the bottom of the board, we'll notice there's an output harness to the hot surface igniter, the HSI, and the inducer fan motor. As we move around the board some, we see we have a 12-pin harness, and that's going to be 24-volt inputs and outputs to key components like the pressure switches, the rollout switches, the high temperature cutout switch, and so on. And the gas valve will all be harnessed in on that 12-pin harness. And so if you take a look at your install information and your technical information, you'll see that there's some schematics and stuff in there that you can get more detailed on pin to pin. But basically that 12-pin harness is where we have our inputs and outputs to those key components. Like I said, our gas valve and pressure switches and safety circuits and so on. To the left of that, you're going to find a 3-amp fuse for onboard 24-volt protection. So all of our 24-volt components on the board will be protected by that fuse. If you look closely on the silk screen right next to it, it does say 5-amp maximum. We ship it with a 3-amp fuse, but you can go up to a 5-amp fuse if you had some reason to do that. About in the middle of the board, but on the right, towards the right-hand middle side, is our flame current pad. Now, team, if you recall from our last training session, you'd notice that the flame current pad was at the bottom of the board on our last training session. So please notice that on this particular board, the flame current pad, it does the exact same thing. If you take your voltmeter and you go between those contact points on the flame current pad, if you take your voltmeter and put your voltmeter to DC volts, you can actually read flame current on that pad now, but it will come out as voltage DC. So 1 volt DC on your DC voltmeter is equal to 1 amp microamp DC flame current. So unlike our competitors that make you take the little wire off and have a special meter and all that stuff, you don't have to do that anymore. So you don't have to have a special flame current meter anymore. You can use just your standard voltmeter and put it on DC volts, and then when you read between those contact points on the flame current pad, 1 volt DC is equal to 1 microamp flame current. So it's really simple and easy to read flame current now on the boards, and all of our Johnson Controls Champion products feature a flame current pad. I just wanted you to make sure and you took notice of it being in a different position than where it was on the previous board in our last training session. We normally have those on our other boards are kind of towards the bottom of the board as you take a look at it. But this one here happens to be about in the middle of the board on the right-hand side, more to the right middle of the board. So just pay particular attention to that. And this is a very important thing that we're going to be talking about here shortly as far as flame current and testing flame current. And so that's where you would do it on this board. Any questions or comments on the layout of the board before we talk a little bit about testing flame current and heading towards the end of our training session? Any questions or comments?
Yeah, I is that an echo?
Go ahead.
Okay. So earlier you were talking about being capable of putting a 5 amp fuse onto this board, and I was just wondering, under what circumstances would somebody be inclined to do that? Like, would that be if you had a number of accessories going, utilizing the power of the board, such as, humidifier and UV light and, an electronic air cleaner, things like that? Or
That's an excellent question. So we give you an output for the humidifier and the electronic air cleaner. We give you an output for that.
yeah.
But an example is, let's say you had a local requirement. Let's say you had a local code requirement that had to have some sort of air proving switch or something like that, that would that was going to be on the 24-volt side, or maybe you had some other accessory, to your good point, on the 24-volt side that would load that up all. But that would be the only reason you'd ever do that. Your good point. Excellent. Good question. Any other good questions or comments? Okay, team. Well, let's talk a little bit about testing flame current and measuring flame current. And guys, this is really important. I like to think that every time you do a service call, or every time a technician does a service call, they should probably check flame current just to make sure it's not degrading from the last service call. As a matter of fact, I recommend, when you do your service calls out there, to go ahead and mark down on your service ticket what your flame current was. And then next year, when you go do your clean and check the following year, you can compare to see if it's changed. And so this is an important skill that every technician needs, is to know how to measure flame current. And so we're going to talk a little bit about flame rectification and the science behind it, and then how we're actually going to measure flame current on our control board as we kind of wrap up the session and open the floor up for some questions and answers, or questions and comments. So flame rectification it's a pretty simple process. It's quite brilliant, whoever came up with it. But what it is anytime we have power to the board, we have AC voltage going to the flame sensor. Now, it should be noted this is line voltage driven. And so what I mean by that is this: if you've got 120 volt to the control board, there's going to be 120 volts or very close to it on the flame sensor. Now, catch this though. This circuit is an extremely high resistance circuit. We're talking hundreds of millions of ohms resistance. So there's no current to speak of there. So in other words, if you touch that flame sensor, it's not going to shock you. If you shorted the flame sensor to the side of the burner, or if you were to short the flame sensor to ground, it's not going to burn anything up. It's not going to pop that. It's not going to pop that 3 amp fuse. It's not going to pop the main fuse or the breaker on the furnace, because it's an extremely high resistance circuit, although there's 120 volt on that flame sensor. So if you were to take your voltmeter and check that flame sensor to ground or neutral, you'd see, golly, there's, your voltmeter, based on the quality of your voltmeter, you're going to read anywhere between 90 and 120 volts on that flame sensor. So the flame sensor has AC voltage going to it all the time. Anytime there's power on the furnace, you're going to have AC voltage on that flame sensor, but there's no current flow. And so at this point, nothing happens. It's just an open circuit. However, when you build a fire, or you start a fire, so to speak, what happens is that AC voltage goes through the flame sensor and through the flame itself to the burner. Now, the burner is grounded on chassis ground, and the control board is also grounded on chassis ground. So that AC voltage actually goes through the sensor, through the flame, and then it's rectified. The flame itself actually acts like a rectifier. And so what it does, it cuts that voltage in half. Now, it isn't a perfect circuit. That's what they call a poor rectifier. But that AC voltage goes through the flame, and the flame actually rectifies or converts that AC voltage to a pulsating DC voltage. It then takes that pulsating DC voltage, it passes through the flame and the burner, and it actually puts that DC voltage on the ground plane. This is why it's so important that we have a really good solid ground on our furnaces, and the flame sensor has to be clean. Now we recommend to clean that flame sensor with steel wool. I like to use stainless steel wool. Do not use sandpaper because you can leave little pieces of sand on there. And so don't use sandpaper, but use something like steel wool or Scotch-Brite to clean that flame sensor. And so that AC voltage has to have a nice clean path to go through the flame to chassis ground. And then that DC voltage that's actually provided on the chassis ground is going to be monitored by the control board. And if it sees or if it senses DC voltage on the ground plane, it knows there's a flame present. And so as long as it sees that, it will allow the gas to continue to flow and so on that. So that's the science behind flame rectification. We take AC voltage, run it through the flame rectifies it, and dumps pulsating DC along the ground plane. Now, it should be noted, one of the things that's really, really important, again, you have to have a good solid ground. You have to have a good ground to that furnace, and the flame sensor has to be clean. In addition, the polarity on the furnace has to be correct. In other words, if your neutral and your hot wire are reversed on your power coming in, the board is not going to be able to see the fire, so to speak, because of polarity. So polarity has to be correct, good solid ground all the way to earth ground, and then a clean flame sensor. Those are very, very important in order for our flame sensing circuit to work properly. Any questions or comments on the basic science behind flame rectification, how it works electrically, and then we'll talk about how to measure flame current here in just a minute or two. Any questions or comments? Okay, well, team, measuring flame current. So here's a little picture. I kind of cropped the picture of our control board that we're talking about this morning, our TMY. And remember, our flame current pad on this particular control board is kind of in the middle towards the right, around all those relays on the board. And so what we're going to do, we're going to call for heat. Step number one, we're going to call for heat, W or W2, either first or second stage. In other words, it doesn't matter, but call for heat and let the furnace establish a normal flame. Then we're going to set the meter to DC voltage on the lowest scale that we have. And we're going to measure the DC voltage on that flame current. Now remember, team, 1 volt DC is equal to 1 microamp flame current. And again, please remember and notice the difference of where that location of that flame current is. That flame current pad is on the board. It's in a little different spot on this board. And so 1 volt DC is 1 microamp flame current on the board. Now it should be noted, if the flame current falls below 1.5, if it falls below 1.5, you're going to get an amber flash code on our little LED that's telling us we have low flame current. Now write this down and remember it. Amber flash code starts occurring at 1.5. The furnace will continue to run all the way down to 0.1 microamp flame current. So that's very, very low, 0.1. It'll continue to run. So our lockout point is 0.1. 1.5 is where we generate an amber flash code to let you know, hey, the flame current's getting low. Typical flame current, normal flame current generally runs about 3 to 4. And so if you take a look at your install manual, I think it says 3.5 or 3.7 is normal. But my field experience and, just hearing technicians in the field measuring flame current all the time, it typically runs about 3 to 4 based on the quality of the ground and if the flame sensor is clean and you have a proper gas pressure and the flame is you have a good solid flame and a good clean ground and so on. So, but just remember those kind of key points. 0.1 is lockout. 1.5, you get an amber flash code telling you, hey, it's starting to get low. And then typical flame current typically runs about 3 to 4. Any questions or comments on what we've talked about this morning? Let's go ahead and open the floor up for any questions or comments, and then we'll kind of round out with those good questions. And if we don't have any, we'll go ahead and conclude for the morning, but go ahead and open up your mics if you have any final questions or comments. Everybody good? I can see you guys on the camera. Do we get a thumbs up this morning? All right then. Well, team, I'll tell you what, I want to thank everyone very, very much for your attendance today. We love training with you, and we'll continue to do this, and thank you for the opportunity, and we certainly look forward to training with everybody again.
Thanks, Joel. Have a good day.
Thank you. Everyone have a good day.
Thanks, Joe.
And we'll be posting this out on our YouTube training channel a little later on this morning. Have a great day.